All right, so you warmed up by trying 2 of these on the bottom. So I am just going to make the assumption that y'all did the first 2 or the last 2.
All of it.
So then we're going to review the first 2. Sounds good. All right, just to make sure we've got this. So real quick, what was being represented here? Like how do we come up with this first picture? What do you have to think about? Your valence electrons. Good. And what was this showing in this thing? Like why? I know it's the transfer, but what is this showing it becoming? A cation and an anion, right? So here we're actually showing the cation here. He lost all his electrons. This guy gained that extra electron, so he's an anion, okay? And remember, we have to keep that ratio clear, right? So we have to make sure we have enough places for those electrons to go. All right, so just to kind of review it real fast, I'm just going to show you this. So we had potassium from group 1, so I put 1 little dot over him. I have fluorine from group 17, so I had 7 dots around this one. And the dots are going to be important today, okay? That's why we're reviewing this real quick. Okay, so I put brackets around him, show the transfer, and I end with a potassium with a positive charge, a full fluorine. Remember, some of your points come from that, so make sure you put all your electrons around it with a minus symbol, okay? And that's it. All right, and then you would show your KF, okay? And then for something like the magnesium iodide, you had magnesium, put 2 dots around magnesium. You would make your iodine, and you would have 7 dots around that one. You would see that that doesn't finish the transfer, so you had to make another iodine to do the last transfer, and then you draw everybody. Okay?
Wait, how many dots does iodine have?
He has 7. Group 17. I'm going to do lines, sorry. And then you draw the other iodine. All right, so how many of you guys did it the classic way? Like you just did it this way when you did it, okay? How many of you guys went and did your little crisscross first so you could figure out how many you're going to have to draw? Anybody do that? No? Okay, well, you have that skill now. You have that in your back pocket, so feel free to use it when you come to exam time and you need to know how many of these guys you have to draw, right? This would be Mg with a 2 plus, I with a minus, crisscross them, you have Mg, I2, right? Okay, so we're all good on this? Ready to move on? Sweet. Turn to that has Lewis theory at the top, so it's towards the end. Okay, so with the Lewis theory, all that we're talking about is these bonds, okay? And the whole idea of what a chemical bond is it's the fact that these 2 atoms get close enough to feel some sort of an attraction, whether it's electrostatic or it is having to do with their electronegativities, and they're kind of bonding to where they're going to share, right? So that need for 8 electrons, or fulfilling their octet rule. But they get close enough to have that attraction, but not close enough to repel. All right, so it's not. There's a certain distance for every single bond out there, and you guys are going to pay attention to that a little bit today. Okay, so real quick at the top though, I want you to put this. We're not going to focus too much on it this time around, but after you guys take your little test over naming and drawing, then we're going to go into these details called. Not called, sorry, about like being polar versus non-polar, and it all comes down to their electronegativity. So who remembers on your trends, what was electronegativity? How did we show that trend? What did we put on it? A heart, right. This is your heart. So this is your ability to attract electrons in a chemical bond. That's what electronegativity is, okay? And so these differences in electronegativities is what causes those different types of bonds. All right, and that's what you're going to see. So it all comes down to electronegativity. So this whole idea where I'm like, oh, this guy wants this many and wants to steal this many, this guy wants to give up this many, that's me. You guys know what personify means? Yes. Like I'm making them like alive. You really shouldn't think of it like that. It really actually comes down to electronegativity, which is that ability to attract electrons. Okay, I know that's kind of boring, but remember, whenever you're writing your answers, don't ever do it wants this. No, they don't want anything, okay? Are we all clear on that? Because I saw that on a lot of your guys' free responses for the benchmark. Don't talk about wanting. It's not that. All right. So looking down this little list, you have a couple definitions here. And so big idea was we know that in the last drawing, we saw that transfer, right? So ionic bonding is specifically about a transfer. Covalent bonding, today we're going to see is sharing. And they share it in a bond, okay? It's a covalent bond, right? And so today we're going to do this little equation, and you got to know that when I say the word sharing, I'm talking about how many bonds, okay? All right. We also know that valence electrons are really important. You guys saw that with your Lewis dot structures, okay? And don't forget that those valence electrons are coming from your electron configuration. The fact that you have the S block has 2, P block has 6. When you add them together, that's the octet rule. That's the 8 electrons that we keep talking about, okay? But what that should also tell you, so let's write this off. So a full shell. Okay, so we know that when we get lower and lower on our periodic table, you start having probably more in that outer shell. We're not going to deal with that in Chem 1 though, okay? Don't worry about it right now. But a full shell is satisfying an octet rule. However, does the top row, the very top row, the one with hydrogen and helium, does that have a pink room or a P block? No, right? So we have exceptions to our octet rule. And we're going to write them here. We're going to write them on the next page. We're going to write them on the next page so you don't forget them, okay? So exceptions to your octet rule. Hydrogen and helium only need 2. Okay? And that one's pretty obvious because you can see where they are on the periodic table. The next ones, I'm not going to go into detail as to the why because y'all don't need to know that right now, okay? But the next one is beryllium. Beryllium only needs 4. Okay, so he has valence electron of 2, so he just needs to pair them up. And the last exception is boron, who only needs 6. So boron has 3 valence electrons. It just needs to pair those guys up. Okay, so these are the exceptions that you need to know for today. Okay. All right, any questions on that? Look at the bottom of your page now. So this is just a reminder, or just a little visual on that, right? So those you guys have been practicing, here is the beryllium, circle this guy and this guy. So you remember that those guys are exceptions. You just need to pair them up. Then you see that when you get to carbon, that's where octet rule starts. Do you guys kind of see that here? Okay.
Is it just those two?
Yep. Not lithium. Yeah, just hydrogen, helium, boron, beryllium. Okay? All right. Cool. So, moving on. Yeah, turn the page. Sorry. All right, on this page, I'm not going to go into much detail. I just wanted to point out you got Coulomb's law here. Okay? This is how ionic bonding is happening, the whole idea of the cation, anion. So a positive charge and a negative charge at a certain distance have some sort of a force of attraction. Okay? So that's something that you guys have been already working on. And then this is just showing what you guys already did. Flip your packet over. Look at this page. That was it, yeah. Huh?
There, she didn't say anything about that. It was only
Oh, the end is just showing that transfer again. It's just showing it with electron configuration. All right, so up here, I want you guys to actually, I'm going to flip on the light so you guys can look at it. I want you to look at these 2 charts. And I'm going to have you focus on 3 things. I want you to look at when you have a single, double, triple bond, how does that affect your bond length? I then want you to look at oxygen and sulfur and tell me about that bond length. And then I want you to come over here and look at how bond energy is affected. So I want you to come up with kind of 3 conclusions looking at this data. And you can work with a partner. I'm going to give you about 1.5 minutes. So I want you to look at those things, come up with either a trend or an idea, okay? So take 1.5 minutes. All right, so let's kind of come back together here. So underneath these, what I want you guys to write, okay, is we're going to say, as we move from a single to a triple bond, okay, and you guys hopefully noticed that some of those had more than one line in between them, okay, so as you move from a single to triple bond, Okay. What happened to bond length between them? It decreased. Good. So these guys got closer together, right? So they kind of just squeeze in a lot tighter because you got a lot more force there. Okay. What happened to bond energy? It increased. So real quick, what this energy is talking about is energy needed to break it apart.
Sort of like the ionization.
Kind of like ionization energy, exactly. All right, so this bond energy is needed to break it apart. So you can kind of see that a triple bond, what would you say? Is a triple bond stronger or weaker than a single bond?
Stronger.
Stronger. All right, and that's going to play a role in some of the characteristics that you guys are going to see, okay? Now let's talk about this little trend here. What did you guys notice? Or did anybody come up with a conclusion about that? Why is oxygen closer than sulfur? Yes?
Oxygen is more electronegative than sulfur is. Okay.
No, not quite. Not quite what I was going for. What happens on the periodic table between oxygen and sulfur?
Sulfur.
Yes, sulfur has one more shell. So who's bigger out of those two? Sulfur is, right? So that distance is going to increase. And that's what I wanted to get you guys to see, is that atomic radius is still going to play a role. So if we were to hook it up with francium, that would be like a huge distance, okay, versus something that's all in the top row, okay? So that's also going to play a role in your bond energy. And you can actually kind of see it. It's not so big between those two, but we'll see it later, okay? So the ones that are really far apart are a little bit easier to break apart than the ones that are really close together, okay? So I just wanted you to know your trends still aren't going away. All right, cool. Now we get to learn NAS. Yay, you guys ready? Yeah, yes you are. All right, cool. So the NAS rule, all right? The NAS rule stands for, you guys are going to write this down, okay? The N stands for needed. A stands for available. And S stands for shared, okay? Now, we are going to use this method on some really easy ones that honestly, you could look at their Lewis dot structure and put them together and you would have been fine. But I'm going to force you to use this method on all of them so that when you get to the hard ones, you'll start finding, it'll be easier, first of all. And second, you'll be able to recognize when you need a double and a triple bond. And third, when you get to the really, really higher level ones, because I am going to put some AP ones in front of y'all, you're going to see exceptions to this octet rule. And some guys are going to get like 14 electrons around them, all right? And so I want you to be able to use this method so that you can see what you're supposed to do, okay? So please use this. Do not cheat, okay? All right. Let's look at this little paragraph thing. So it says the Lewis structure of molecule-based octet rule can be predicted using a set of rules that take into account the number of electrons needed, okay? So when we say needed, okay, all of them are 8. Where do I want you to write this? I'm going to write it above it. So 8, except for who? Hydrogen needs what? 2. And boron needs 6. And beryllium needs 4. Okay? Why did I leave helium off of that?
Because it already has the full shell.
Is helium really going to bond with anybody? No. All right, good. So you guys said it already had a full shell. Exactly. All right, cool. The number of electrons available. Where do you think we find that information? What is that also known as? Valence electrons. Good. Okay, so this is going to be your valence electrons. So it's going to be important to look at what group they're in on the periodic table. Okay? So group 16 is going to have 6. So I know I've drilled it into your head about the charges. Remember, we're switching over to molecular now. Charges don't matter for molecular. What matters for molecular is their valence electrons. How many total do they have? Okay? And then predict the number of electrons that are to be shared. All right, when we say shared, we are talking about things that are going to get bonded, okay, or the bond. All right. So looking at an example here, you can kind of see the N is going to be needed, so 2 for hydrogen, 8 for all others, and then we already talked about the other exceptions. You're going to see that we're going to do a subtraction, all right? So you're going to take that needed, and you're going to subtract the available. Once you get that, you're going to find out that's how many electrons have to be shared. So that's how many hands are being held between these little atoms, okay? Then you're going to divide it by 2, so circle that, because that tells you what? How many what? How many bonds? Exactly. So 2 electrons in every bond. 2 electrons per bond. That's it. There is no such thing as, so think about it. You can't hold hands with like 2 and 1, right? That's like weird. It just doesn't fit right. Some people do. I guess you could hold their hand like that. Never mind. All right. Anyway, that's beside the point. So it's only 1 and 1. Okay. And then the central atom. All right. So this is also the biggest thing people have trouble with, because you're like, yeah, I know I need like 4 bonds, but who goes in the middle? All right. So this is your rule. Carbon, always. Okay. If you have carbon somewhere in there, carbon goes in the middle. He's the friendliest one up there. He's the plus minus 4, right? So he's just, everybody wants carbon. Even if you have 3 carbons, put them in a chain. It's called a carbon chain. So those of you in AP Bio should be hearing about that, okay? So you put the carbons in a row, okay? But carbons go in the middle. Otherwise, it's your most electronegative. So that's where your trend comes into play. And you got to remember who's closest to that big heart. Okay? There. Is that better? See somebody else squinting. Okay. So most electronegative. I will also say a few of my students in the past, sometimes if they just are trying to rush through it, they put the oddball in the middle. All right? So if you have a bunch of one thing and then you have one more thing and then you have, I don't know. You just put the one that looks like it should be in the middle, which I know it doesn't help, but they say that works for them. I don't use that. I do this. So, okay? All right, cool. Flip the page. Let's look at these examples. So you guys have the examples written. So what I would do is watch me, okay? Because I'm going to actually do it off on the side, really big here, okay? So go ahead and watch me. So I'll flip off the lights so you guys can actually see it a little bit better here. But you guys don't have to write any of this down. You can just kind of follow along with what they've got. So this first example that you guys have on your page is CH4, okay? So you have CH4. So I'm going to look at this, and I'm going to, who goes in the middle for sure? Carbon. Good. So I'm going to put carbon, I'm putting H here, H here, H here, H here. So you're kind of limited to 4 sides for everybody, okay? All right. Now I'm going to run through the NAS. So I'm going to say N minus A equals S. Okay. So needed. When you are looking at needed, we need to know how many does each of these guys need, right? How many does carbon need total? 8. The answer is either 8, 2, 4, or 6, right? That's all that you have for octet rules. Okay, or full rules. All right, so carbon needs how many? 8. How many does each hydrogen need? 2. So you could write it out like this. You say 2 plus 2 plus 2 plus 2, or you could have done 2 times 4, right? Let me erase this so it doesn't look all scary. I'll draw it below. All right, so we have 8 plus 2 plus 2 plus 2 plus 2. What does that equal? 16, good. All right. Available. How many does carbon have available? 4. It's in group 14, good. How many does each of the hydrogens have? 1. So I'm going to say 1 plus 1 plus 1 plus 1, or 1 times 4 is fine. Okay. So what's 4 plus 4? 8. Okay. Now I'm going to do my little subtraction. 16 minus 8 is equal to what? 8. Okay, so I have to share 8 electrons among this. I'm going to divide that by 2 to figure out 4 bonds. So now, going back to my picture that was already there. Oops. Okay, I had this already set up for me. I'm going to go 1, 2, 3, 4, and I'm done. Okay, but the thing to check is that you have 4 bonds. You have to make sure you have 8 electrons accounted for in this picture. How many electrons does each bond hold? 2. So you have 2, 4, 6, 8. We're done. Okay, so this one's kind of straightforward. Okay, Another thing to point out, hydrogen will never get extra electrons. It's bonded. That has 2 already, okay? So biggest mistake that I keep seeing is people like to put extra stuff on that. All right, so let's look at the next example. You have something like water.
Wait, why'd you divide it by 2?
Because there are 2 electrons in every bond. So if you have 8 electrons you have to share, we're going to divide it by the 2 to figure out 4.
It says H2O.
Yep, so fix it, because you guys are smart enough to do that. You guys know what water is, right? Yeah, all right, cool. So fix it on your page. All right, so it should say H2O. All right, cool. So we're going to start here. So looking here, though, who's going to go in the middle? O is, right? And so we know we got some hydrogens, okay? I've drawn it before, that's why I put the hydrogens a little bit lower, okay? But you guys will see why in a minute. All right, so N minus A over S. So needed. Each of those hydrogens need what? 2. So I have 2 plus 2 plus, what is the 8, or the O need? 8. So 4 plus 8 is what? 12. Good. Available. How much does each of those hydrogens have? 1. So I have 1 plus 1 plus, what does oxygen have? 6. Don't talk about charges. Remember, charges is ionic. This one we want valence. Okay? You guys are going to have to switch your brains on and off to that. All right, cool. So I got 6. Ooh, that is not a 6. There we go. What is 6 plus 2? 8. So what is 12 minus 8? 4. So I have 4 electrons that need to be shared. What do I divide it by? 2 to get how many bonds? 2 bonds. Cool. So that makes sense for a picture. You'll see that it usually makes sense. Okay. So I have 2 bonds there. But how many electrons do I have to account for?
4. 12.
The available. It's always the available number. So I have to have 8 total. Okay, so after you've drawn your bonds in, I need everybody to always go back up to your A. Your A is the number that you need to pay attention to. Because this right here, in this step, this is where you're either going to have your rule fall apart or it's going to work. And if it falls apart, that means it's probably an exception to an octet roller. It's probably an exception to something, okay? So you always go back, check your A. How many do I need to account for? 8. This bond has how many? 2. This one has 2. So I'm at 2, 4,
So you have 5.
6, 8. Okay. So on your paper, you guys have it drawn for you already. Circle one of those things. Label this. This is a lone pair. Your electrons have to be in a lone pair. You may not have a single electron floating around. Okay? You have to have it in a lone pair. Because what that does is it satisfies that octet rule. Did you notice, did I put anything on my hydrogens? No, because they're already full. They got those 2. Okay, and this one has those 2. And then oxygen gets 1, 2, 3, 4, 5, 6, 7, 8. And everybody's full. That's the point of a covalent bond. Okay? Where did I get the 6 from? Oxygen. Oxygen is in group 16, so he has 6 valence electrons. Okay? Where did I get the 2 from? Which one?
Step N.
These 2s?
Yeah.
Each hydrogen needs 2 to be full. Okay? So remember, the N, it's either 8, 2, 4, or 6. 8, 2, 4, or 6. So pretty much it's always 8, unless you have hydrogen, beryllium, or boron. Okay? Okay, cool. Flip your page. Look at your examples that you guys are going to work on. All right. So you guys are going to do one with me, and then I will set you free. And today I do need everyone to at least try 4 or 14. For sure, for sure. 13's kind of fun too. Okay? So end goal though. Don't start with those because you don't want to. All right, I'm going to turn on the lights so you guys can see. Okay. So let's do something like F2. Okay, let's do that one. Okay, so I'm gonna do my NAS off to the side and I'll draw my structure in the middle. So I have two of the same thing. So I don't have to worry about a central atom here. Okay, I'm just gonna draw my two F's so I'm ready to go. Okay, then I'm gonna go N minus A, S. All right. And I think you guys have enough room to write that. Yeah, just write a little bit smaller over to the side. All right. So your N, so needed. How many does this fluorine need to be full? 8. How many does the other fluorine need? 8. Okay, so we got 16 for needed. My available, they're both in group 17. So how many does each of them have? 7. So we got 7 plus 7 is what? 14. Good. 16 minus 14, 2. What do I divide that by? 2. So how many bonds? 1 bond. All right, cool. So, am I done? No. Who do I go back and check? Your A. Good. So I need to account for 14 electrons. How many does this bond show? 2. 4. Yes. 6. 8. He's full, so I have to move over to the next guy. 10. 12. 14. Now I'm done. So what NAS also helps you do is not assume that this one has like a quadruple bond or something like that, okay? Use NAS so you know exactly how many bonds are there and how many lone pairs you have to have.
How come we did 14? Because it should be 12 because the dash in the middle is already 2.
Right. So I said 2, 4, 6, 8, 10, 12, 14. Oh, okay. Thank you. Thank you. All right. So I'm going to set you free. You guys are going to try this. What first period did was they opted to either work on a separate sheet of paper so they had more room, or they used a whiteboard. You're more than welcome to do either of those, or just fit it on your page. Okay? All right.